Hi, everybody. Welcome again for the next session of the NeSy Alan Turing Institute talk, virtual talk. We're really happy to have Luke on board today. Many of you might have known or know about his work on statistical relational learning and Neurosymbolic AI. He's a full prof at KU Leuven, also the director of Leuven.ai. He has got 2 ERC advanced grants, once in 2015 and once in 2023, right, Luke, last year.
Yes.
And a host of other very prestigious fellowships, such as the AAAI fellowship. So we're really happy to have him here, and take it away, Luke.
Okay, thanks a lot for the kind invitation and the kind introduction, Vaishak. It's good to be here. I'm going to talk about how to make logics neurosymbolic. And I should stress this is joint work with a lot of my collaborators, especially Giuseppe Mara, and many of the others that are actually on the slide. The motivation for neurosymbolic AI is, in my opinion, twofold. On the one hand, you want to mix symbols and sub-symbols, and on the left you see like an example where there is a lot of perceptual data, the typical kind of input for neural networks and for neural networks tasks. And on the other hand, there is like a mapping to be done to like the symbol level, where you have classifications to be done, like pedestrians, cars, cyclists, and so on. And what's especially of interest for neurosymbolic AI is that there is a balance between data and knowledge, in the sense that the current focus in AI is very much on data, but data is not always available, and even if it is, it's not always useful, because we want that also our knowledge that we already have is respected and is used. We don't want to relearn what we already know, and in that regard, Neurosymbolic values very much the ability to specify constraints, to specify additional knowledge on the task for learning, in order to get the best of both worlds, in a sense. The more data you have, the less knowledge you need, and vice versa. It's also the case that in Neurosymbolic AI, the knowledge doesn't have to be complete. It also doesn't have to be consistent. Basically, what you know, you can write down, typically in a kind of formal language, and then you can kind of start learning. It is like one example. It's a very motivational and inspirational data set to look at, because it really specifies what Neurosymbolic is about. Here is another example from one of my colleagues, Thias Guns, and what he is actually showing is like his Sudoku assistant, which kind of takes an image of a Sudoku puzzle and then is trying to kind of solve it. But the Sudoku puzzle is also like, recognizing what is written in the puzzle. And even there, if you have like high accuracies at the level of individual entries in the Sudoku puzzle, that doesn't guarantee you that you get the whole puzzle right. And it's actually beautiful results that if you just, use the classification, use, the standard kind of neural networks to predict which numbers are in certain squares, and you then solve the puzzle, that you get about 25% of the puzzles correct. But if you kind of use knowledge in that process, and knowledge is here taking the form of the Sudoku rules, that you get much, much better performance. You get like up to 99%, basically, because then you're not individually classifying the instances, the digits correctly, but you're kind of doing joint optimization in the light of what you know, in the light of the knowledge. Today, there's also like the state of the art in Neurosymbolic AI is very much similar to what we had about 20 years ago in the days of statistical relational learning, statistical relational AI. There's basically an alphabet soup of systems, and they all do claim to do different things. And they all show, my system can do a little bit better than your system on this or that data set. But if you kind of take a little bit of a distance, then there's a lot of similarities between these systems. And there's like a common core that we've tried to identify in the survey that appeared in AIJ, in AI Journal, and that we've given a couple of times at key conferences. I'm also going to try to explain the key lessons of that, basically. It's this what leads to a kind of methodology for neurosymbolic AI, because many of these systems, if not all of them, can actually be seen as like being derived with a particular recipe, the recipe that I will be trying to explain. And it's typical for the state of machine learning that people, when they publish papers, they stress what is different, but try to, well, hide away, in a sense, what is similar in order to increase the acceptance chances. And that's not healthy for a field like machine learning and like AI. Traditionally, neurosymbolic is also seen as encompassing neural networks, of course, and then symbolic methods, typically logic, and that's what it typically is. I feel that you also need to include probability. Probability is, you need the probability to bridge the gap between the discrete level of logic and the continuous neural networks. And you can interpret probability in a broad way. People have also been using fuzzy as a kind of alternative for probability. And there's also like many systems that do that. There is a caveat, a catch though, that I will be talking about later, in the sense that fuzzy often has some problems, semantic problems and problems with gradients, as has been shown by Emil van Krieken. Yeah, so the second message that I want to bring is that, well, given this background that I have in going from logic to logic and probability, and from logic and probability to neurosymbolic AI, that I feel that there is a lot of commonalities between this probabilistic logics and this neural logics, and essentially many of the same problems and many of the same solutions that apply to probabilistic logics, to StarAI, also come back in neurosymbolic AI. And that's a very good situation, because we can basically reuse the solutions that we developed there. And the third message is that I'm going to provide this kind of simple recipe for what I believe to be the most interesting category of neurosymbolic AI systems, according to Henry Kautz. I mean, Henry Kautz has like a classification with 6 or 7 categories, but the most fancy one is that where you build deep interfaces between neural networks and symbolic methods. And these are deep interfaces in the sense that the communication goes in both ways. You can go forward, backward, and so the symbolic level influences the neural and vice versa. And you also retain the key expressivity of both the neural component and the symbolic component. And that is typically what I want if I combine two different paradigms. And I guess this interface layer is another pipeline. I mean, pipelines are for plumbers, and they go in only one direction. So let me go through a little overview of the talk. I'm going to provide first a little survey, kind of the key points of our in-depth analysis of the field. Then I'm going to talk about the recipe, and then I'm going to give some illustrations with yeah, some of our systems, especially DeepStochLog and DeepProbLog. So let's start with the little survey. And as I said, I'm very much inspired by statistical relational AI, and statistical relational AI is extending logics with ideas from graphical models. And with like 2 versions of this. One version is very similar to the directed graphical models, the Bayesian networks. And these are the probabilistic logic programs that you can easily write down, and that we've been working on for a very, very long time in this Prolog system. Also, others have worked on that particular paradigm. And these probabilistic logic programs are then kind of, expressive extensions of these probabilistic graphical models. And that's very much the kind of programming perspective, the Prolog perspective, proving perspective. On the other hand, you also have like logic that acts as constraints, and Markov logic is like one of these examples. Also, satisfiability is one of these examples. And Markov logic is like the probabilistic version of constraint specification in a sense, and you then specify soft constraints. They all get a weight, and the higher the weight, the more important it is that the constraint be satisfied. But given that you work with these that you worked with this soft constraints, it's not the case that if a constraint is violated, that a world becomes impossible. And that's like, very much in spirit of Markov logic, Markov networks, and that's like the model theoretic perspective, the satisfiability perspective, if you like. Now it turns out that there's also like this two types of neurosymbolic systems. You can use logic again as a kind of program, as a kind of structure to put into or on top of your neural network. And you can use logic as a set of constraints to regularize the neural network. And mainstream approaches to neurosymbolic AI are belonging to one or the other category today. And to see that this is the case, it's kind of convenient to go back to, the very early days of neurosymbolic AI. And the very first approach, to my knowledge, is that of K-band from Towle and Chavlik now 30 years ago. And what they were doing is like they started off with, this kind of propositional set of rules, kind of simple Prolog programs like A holds, if B and Z holds. And they had a set of these rules. And what they would then do is they would turn that set of rules into an AND OR tree. And the AND OR tree is what you see on the right side of the slide. That's actually what you see over here. At that side, you also see that the goal here is to predict A if you have like values for CD and so on the input side. And this is like the purely logical perspective. But what they did is like they viewed this as the structure of a neural network. They turned that AND/OR tree into a neural network, and then did the kind of things that neural network people do, that is make it fully connected, from one layer to the next. And it would also like insert this latent nodes, like this gray node that you see over here. And then they would simply learn. I mean, they would put examples on the input side and try to get the correct predictions on the output side. It was all very, very simple, all very, very limited, but still to see how visionary these guys were, it's amazing that a few years later, they were trying to do the inverse process, like start from this kind of networks and, kind of simplify it into a set of rules that would explain what is in the neural network. So this is just explainable AI avant la lettre. I mean, people invented the term like 20 years later, but these guys already had the insights of doing that. Now it turns out that this kind of process is also what is taken on in some other well-known systems, such as the neural team improver. It's also working like that. You have like these rules, you build up a kind of AND/OR tree, kind of proof trees, and then you start learning. Now, of course, the modern systems have some other key ingredients, and one ingredient that I fancy a lot from the neural team improver is the fact that they have soft unification that is actually indicated here. Like you've got a predicate like grandpa of over here, but the rule says grandfather of. And that doesn't match if you use pure logic. I mean, there's no unification. Grandpa of is considered to be different than grandfather of. But in the neural team improver, there is a kind of soft matching. It's called soft unification, and they would still be able to prove certain things with particular belief factors or belief values, whatever you want to call it. Also, other systems are working in this way. Also, systems, for instance, from the Prolog group are doing that. And that's like the idea of using the logic as a kind of logic program and use that to kind of program the neural network, so to say. On the other hand, you have like the view of logic as constraints. And there's a beautiful approach by Guy van den Broek and his team at UCLA. And it's best illustrated on this simple example that's taken from their paper and presentation, where you have like a typical neural network, and the task is to do multi-class classification. There's like 3 possible classes, and if you have 3 possible classes to predict, well, you basically want only one of them to have like a high value. So this is a kind of pretty undesirable situation that both class 1 and class 3 are having a high value. And of course, you could solve that with a softmax, but suppose for the purpose of the argument that you're not using a softmax, but that you want to kind of constrain your neural network in other ways. And there's, of course, other applications of that. Well, one constraint that you could say is that at the output level, you want only or you want exactly one of the classes to be to fire, in a sense, to be the target, to be the real classification, and you can do that by specifying this kind of simple constraint that has exactly that purpose. And what you can then do is, use the values that are in there and interpret these as probabilities. And with these, you can compute the probability that the constraint is satisfied. And that's a simple manipulation. It's basically what you get there. You get like this sum of products. And that's the basis for the semantic loss. If the probability that the constraint is satisfied is very high, then you don't really need to change your neural network. But if it turns out that the probability is very low, then basically what you want is to regularize the neural network. And that's the basis for the semantic loss, which is beautifully simple and elegant, and it's a highly recommended paper to read. You basically compute the semantic loss and you combine that with your traditional loss function, and that's essentially what this approach does. And again, similar in spirit, there are many other approaches like the logic tensor networks from Serafini and Garcet. Semantic-based regularization from the Siena group are also working in this view of kind of using logic to constrain the neural network. I mean, the term semantic-based regularization already indicates that this is what is being done. And so you have like 2 of these types of symbolic systems. Neurosymbolic systems. One is the neural program, the other is the kind of regularizer. And there is a bit of a downside that in both approaches, you, in a sense, lose the ability to reason logically, because everything disappears in the structure of the neural network. And so what we typically fancy is like a different approach, because I believe that if you integrate 2 different paradigms, that you should get the originals as a special case. And so your neurosymbolic AI system should allow you to reason logically, and it should also allow you to do whatever you do with neural networks. And in our case, we're not looking at just logic and neural network, but also at probabilistic models. So also that is something that we want, and that's again this deep interface between the different components. So the recipe that I can now come to is basically showing how you obtain such logics. And the first step is really, to start from some neural networks. And of course, I'm using a toy kind of example. There is like 2 neural networks for which you know the structure, you don't know the parameters, it's not been pre-trained or anything like that. You get, a kind of signal, you get a kind of image, and you want to predict whether or not there is an earthquake, whether or not there is a burglary. So that's at the neural network that, there are these neural networks. You have your knowledge that is specified. Here, you specify when the alarm goes off. You also specify when somebody is gonna call, basically. And with this logic, you can kind of build the same kind of and/or trees that we've seen with K-band and that we've seen in the neural tier improver. You can build this structure. Now, if you look at that, what you want is basically learn end-to-end. You want to get, as input signals and images. And maybe you may want to know also whether John heard the alarm or not. And then what you want to predict is basically whether John will call upon these observations. What you don't know is whether this is an earthquake, whether this is a kind of burglary. So you only get, what's at that level, basically. And the task is to train the neural network parameters. If you want to look at this so-called distant supervision task, you need to do one more step, one more thing, because we've got the discrete world from logic, and we need to match it with the continuous one from the neural networks. And that means you need, quantities to get involved. And there it's very convenient to get probabilistic interpretations, like in the semantic loss, like in the systems that we develop. People have also used fuzzy, but more about that later. Because if you introduce these probabilistic values there, we can now look at what these neural deep interface is, basically. And this is something we've called the neural predicate. It basically means that you take one of these neural networks and you interpret it as a predicate in logic, and not as just a predicate, but as a probabilistic predicate. And this is the kind of things that you do. And if you do that, what you get is basically that what you get is that, the structure becomes a kind of computational graph by choosing, which set of numbers you're going to use. By choosing your neural predicates, you define also the semantics of this, and you define ultimately the computational graph that will be used. And from then on, you can do, the usual kind of stuff. You've got your semantics that follows from that. You also can do gradient descent, from top to bottom in the classical way. First, from the examples at the top, at the root, then down to the leaves of the tree, and then further down, you can propagate the error down to the weights of the neural networks. You also get very naturally explanations, because, if there is, if it's, for instance, high probability that John calls upon these observations, then, you can also detect why he calls. And that could be because there is a burglary, or in this case, the value for earthquake is very high. And there you can use then the probabilistic logic, in a sense, to provide natural explanations. I should stress there is many variations on this. You can vary the logic, you can vary the quantitative component, you can vary the inference and the learning algorithm. So there is many degrees of freedom here, but essentially many of the algorithms can work like that. It's kind of instructive also to look a little bit more at the way that everything is combined, and to look also at this probabilistic versus fuzzy, and at this kind of computational graphs, because that ultimately defines the semantics of things, and that's also part of the recipe. In order to do that, let's look at this kind of logical formula. A and B imply C. And what you then want is a kind of structure that corresponds to that. The propositions are going to be the leaves of the tree. And then you build up, the expression. There is A and B, and then, A and B imply C is what you get there essentially. And then depending on the kind of logic that you use, the operators will also work. And so there's like this algebraic structure that characterizes your semantics for this. And in the case of Boolean logic, it's very simple. You've got the typical truth tables that will propagate, the labels that are true or false from the leaves to basically the top. In a fuzzy logic, people typically use these t-norms, and there are these three fundamental ones: Lukasiewicz, Gödel, and product t-norms, and they all have like slightly different operations and properties, but they're all kind of continuous and differentiable, so they can be used, and they are being used inside neurosymbolic AI systems. There is a problem with this in the sense that for some of these logics, what you would expect to hold in a logic, like if A implies B and B implies C, it's not guaranteed that A also implies C. So that's like one of the difficulties, that if you rewrite things, you don't always get the same value. And it's also a little bit abuse of fuzzy, because fuzzy is intended as a notion of vagueness. It's not meant as a replacement for probability in that regard. And also, like Emil van Krieken shows that there is a set of problems coming with that. Like, for instance, if you look at this min-max, of course, you get problems with vanishing gradients and stuff like that. If you look at probability, it's also not, so the reason why people use fuzzy is because it's efficient. You don't have to change your circuit. You just build up your circuit, and it is what it is. No need to do anything else. In the case of probabilistic interpretations, you need to kind of compile your circuit into a form so that the probabilities are respected. And that step is a computationally expensive one. You've probably heard Weishak talk about these things at some point, knowledge compilation and probabilistic logics, because that is at the heart of also like graphical models and a lot of these operations. Now, why do you have to do that? Well, it's illustrated by the simple sum, in a sense. If you have like the formula A or B, and you want to interpret it probabilistically, then the probability of A or B is not just, the sum of A and the sum of B, but you also have to subtract the intersection. And subtracting the intersection means that you have to transform the circuit into another circuit, to make sure that the operations at the end will make sense and will be useful. And that's, of course, a hard problem. Okay, so the previous 2-3 slides were all about probabilistic logics or fuzzy logics. Let's now look at what changes if you make them neurosymbolic. Well, here you've got the classical logic. Here you've got the classical probabilistic logic, so to say. And how to make them neurosymbolic according to this recipe. What is being done, in a sense, is that the parameters of these predicates, that they are kind of reparameterized. The probabilistic or the fuzzy values of particular predicates, they come from the neural network. So in a sense, you do a reparameterization of these probabilities and fuzzy values. And that essentially means that the neural networks are coming below from that. And so here you've got the scheme, in a sense. If you go from a logic to, or a fuzzy logic to a neurofuzzy logic, well, this is the way to go. If you go for the probabilistic version, then you actually have to do the knowledge compilation on top of that. So that's the recipe. And I think it can be used to explain many different systems. It's also the way that we've been deriving some systems. I've kind of illustrated it more or less on our DeepProbLog system, which is the oldest one that is coming from my group. There is like two different versions of probabilistic logic programs. One is, based on Bayesian networks, there's probabilistic graphical models, and that's the DeepProbLog that you've seen. In terms of graphs, it's like, about putting probabilities on the on the edges, and then sampling subgraphs from that model and working with this, and that's also at the origin of Prolog. But if you look at graphs, then there's also like the random walk model, and the random walk model results in probabilistic grammars. And that's like the notion of stochastic logic programs rather than probabilistic logic programs that you can get. And so in both systems, well, what you do is you take these logic programs, the stochastic or the probabilistic, and you inject the neural networks. The advantage is that, as compared to many other systems, is that DeepStochLog and DeepProbLog retain the full expressivity of these Prolog programming languages. So you get a programming language. A second one is the kind of design choice criteria that I wanted, is that you have both logic and neural networks as special cases. And the final one is that you also got a very well-defined semantics, which is often, or which is not always that clear with many of the other systems. I mean, they perform some optimization, but what is the meaning of what they represent in a sense? That's not clear for all the systems that we have. So I'm going to illustrate the recipe on DeepStochLog. That's starting actually from context-free grammars, which we all know from our computer science courses, I presume. So on the left, you have like the context-free grammar. There is like this non-terminals like E, P, and N, and so on. And there is the rewrite rules. And then you have the terminals like plus 0, 1, and so on to 9. And given such a grammar and the string, you can find a parse tree that actually explains that in a sense, proves that this is part of the language accepted by the grammar. Now, context-free grammars are beautiful and have been studied for ages. And there was like two orthogonal extensions of these grammars that have been introduced for a long time and that are well known. So like one is the probabilistic versions of that. What you do in probabilistic extensions is for every set of rules defining one non-terminal, like here E, there is a set of parameters that sums to 1. And you see it also here for N. They also sum up to 1. And then you get like this parse tree that you can now annotate with probabilities in a sense. Whenever you apply a rule, you just note down the corresponding value, the corresponding parameter value of your rule. And at the end of the day, you multiply all these numbers, and then you get the probability of the parse tree. And that is kind of useful because it allows you to select the most likely parse tree, the most likely interpretation in the sense of the sentence. And the second thing is that unlike what happens in graphical models, here, if there is like multiple parse trees for one sentence, the probability of that sentence is just the sum of the probabilities of the parses. So you don't have to do this knowledge compilation. So it's much more efficient. Inference for PCFGs is like cubic. That's the famous CKY algorithm that you can apply. The other orthogonal direction on extending these grammars is with unification. And essentially what you do here is like unification is meant, for instance, to enforce agreement between the subject and the verb. That should be like, both in singular or in plural form. Here it's used in this little example, you had to pass on the value of the expression that has been parsed. And that's actually what we've got over here. And then, of course, if you have like two orthogonal directions, it's kind of interesting to combine them. And I guess that's the key insight that Steve Muggleton did when he invented his stochastic logic programs. And that combination is essentially what you see here. Now, what we have is we've selected our logic. That logic is, grammars. We've selected our probability. The probability value is like the probabilistic extensions of the grammars. And so the remaining step is now to introduce the neural networks. And again, we can do that by introducing these neural predicates. The normal neural predicates, what they do is they take, certain inputs that can be an image like here, this classical MNIST, and it then produces a kind of probability of belonging to a certain class. And then that kind of expression is inserted into the logic that will give you the kind of leaves of your tree. And you can also do that for this neural definite clause grammars, this DeepStochLog, as we call it. We just allow that at least. We now use a neural network, and we also use like images that represent this, and then you can use directly this little grammar to kind of learn, from this type of expressions, what the value ultimately should be. And so what is learned here is like the parameters of the rules and the parameters of the neural networks. These are not given before training. They are actually learned from data. You can do lots of things with that. You can, look at sequences of these numbers and add them. You can look at this kind of expressions. You can also apply the setting to traditional tasks like, link classification. You can do things on SQL to get guarantees that the outputs. So here, what we did in this application of DeepStochLog to SQL is the input is like a natural language sentence together with the database structure of the that you have. And then, what it should do is output a SQL query that is executable on that database schema. And that was a paper published at last NeSy very recently in Barcelona, showing this kind of approach. There's also like many other extensions that we have been looking in our extension of deep probabilistic logic, so of DeepProbLog, called DeepStochLog. We've been also looking into this soft unification that was in the neural tier improver, and really look, at how you can do kind of soft matching between things like, France and the flag and this kind of stuff. What is nice also is that there's here like a little semantics and criteria that and some theorems that show when you get reasonable framework for soft unification. And you can interpret it as a kind of probability distribution. You can interpret these things as neural as probabilistic predicates. The fact that things are the same, like that France and this is kind of connected. You can interpret it as the probability and then do the usual stuff in these probabilistic logics. We've also looked at continuous distributions, also at generating things like For instance, trying to ask this kind of question. There is work by Mizoni and et al. At NeurIPS, also by Leonard at UAI, where you can take this kind of queries and then generate like also the images, so that if you take the image and you would sum the values together with the first value, that you would get a 5. So you should get 4s here. And there is even like in this val system from Mizoni and others, you see that it can even take into account, the way that things are written. So like whether it's written in this style or in that style, you can make the style, so to say, consistent. We've also used these probabilistic logics in reinforcement learning as a kind of shields, and to say when actions are safe, the probability of an action being safe in a particular state. That is like what the shield should express. And then you can modify your reinforcement learning algorithm to look for safe policies. And that's basically, these modified policies that then, are guaranteed to be safe. So you can condition, in a sense, on safety, so to say. There's other things that we look at and people have looked at. For instance, one nice application is also like recognizing chemical structures from their handwritten kind of drawings. We're looking at kind of automated engineering. We're also very much interested in planning and reasoning, and ultimately in robotics, but there we've done stuff with probabilistic logics, but not yet with the neurosymbolic ones. And of course, there is much, much more than just what we do. Okay, there's many challenges scaling up, but I should say that we've made a lot of progress here, because one of the two components of the DeepProbLog has been sped up with a factor of 1,000 for some of the examples, thanks to the use of GPUs and all that. What is also especially challenging is like theory is missing, I think. If you look at neural networks, then there's like a nice theory that indicates how to develop neural networks and what properties they have. I think for Neurosymbolic AI, there is not so much. And of course, that's interesting to investigate. Okay, let me conclude by summarizing. I believe Neurosymbolic is not just about logic and neural networks, but it's also about probabilistic methods. And you basically want all of them as special cases. We can also learn a lot from what has happened in StarAI over the past 20 years, and many of the problems that arise there and many of the solutions that apply also apply to Neurosymbolic AI. And then finally, I've given a recipe that is fairly general and that can be used to either explain existing algorithms, existing frameworks, existing models for Neurosymbolic, or else like to derive some new models. And that's also what we regularly do. So thanks for your attention. And yes.
Thanks a lot. That was really inspiring. If people have questions, feel free to drop them into the chat. In the meantime, I had a couple of questions, Luke. You mentioned in the beginning that you had done this survey that contrasts different logics and different approaches. And as you said, people often emphasize the differences, but fairly frequently, they don't talk about the limitations or the things that are the same. I was wondering, I mean, keeping in mind how expensive it is to compute gradients with something like any sort of circuit, what is the distinct advantage of an approach that something like DeepProbLog, where you use the program in the computation of the gradients and train the network, versus having a kind of more hybrid and loose approach where the neural predicates are simply components in the logic program? This is the older stuff. from say the 2000s or even earlier than that. But specifically what I was thinking about was, as you know, in Apple Notes, they have this feature where you can write down equations in handwriting and then it computes the answer based on that. And what I was thinking is that what's likely happening is that they're using generative AI to go from image to a mathematical equation. And then the mathematical equation is solved exactly using a solver, right? So I don't know if you have any thoughts about that.
Yeah, so I think the key advantage of the use of these systems like the semantic loss or DeepProbLog is basically that you can use the knowledge to constrain the learning in a sense. That's the key advantage. And in the approach, well, to go directly, to map from language to a kind of formal language and then call a solver. Yeah, that's of course also interesting. And you can also view that in a very, very broad sense as a neurosymbolic AI, but you're not getting a lot of guarantees there. Like with something like DeepProbLog, you get guarantees that the output respects the logic in a sense. That is
Well,
something.
I was thinking along those lines. What I meant is that, for instance, I mean, it wouldn't quite do the task that you did with weak supervision, where you give the label to
Right.
the sum, but not to the individual things. But imagine now you had a perfectly well-built character recognition system, and now I use the iPad to write 0 + 2 + 3 + 4, which is what typically the kind of application one might
Right.
have in mind. And what I was thinking is that each of those characters, handwritten, would be translated into to
Yes.
digits using a neural network. But then I would use a logic solver to compute the
Yes.
sum or whatever it is. So in this case, I do get exact answers because that's almost like, as you say, the word shield. It's almost like a gatekeeper at the very end, right?
Yes.
So
I think
uh,
the answer is to that question is really like if you look at the Sudoku puzzle, because there you do
mm,
exactly this. I mean, if you do just, the transformation, just do the prediction of the numbers, and then you feed it into a constraint solver, 75% of the time you end up with the wrong puzzle,
mm,
with the wrong answer. And that's because, there's a very small probability that, you get one of the numbers wrongly classified, but there's so many numbers that the probability of getting at least one wrong is significant. And that kind of
mm.
propagates through the solver. And yeah, so it's better in a sense to use that knowledge to constrain the process, and you get much better performance.
Mm.
It's you can, in a sense, correct for you can correct some of the mistakes because of that.
But then do you see, yeah, that sounds good. But then do you see any downsides to it? So, I mean, in the work that you've done with your group, have you seen some limits in terms of how big the program can be before you say, okay, let's stop computing gradients because this is getting, too expensive?
Yeah, so I mean, complexity is expensive, is high, and I guess that's where, just like with probabilistic inference, one of the challenges lie. But I mean, I think we haven't really tried enough, and we haven't tried on a large enough scale to do this. And like in my group, they've in relatively short time ported some of the stuff to GPUs, and they got a factor of thousands at the circuit level. So I thought that was pretty encouraging. And I think at the level of logic, one can do, there's also potential to do much, much more. And we also cannot really compare, to this kind of tools like TensorFlow and PyTorch and what else, because that's been developed over so many years with so many
Yeah,
people
absolutely.
at the commercial level, whereas here it's typically going for, yeah, relatively small endeavors by relatively small groups, at least if you
Yeah,
compare to the big tech.
yeah, fair enough. There are two questions in the chat, Luke. I think you
Okay.
may, I don't know if you can see it.
Yes.
And if you could read them out or at least summarize them, you may have to stop sharing.
Okay.
Do you see the chat?
Yes, yes, yes.
Yeah.
What the prior knowledge of DeepProbLog is? Well, the rules are specified. That's basically it. And also the structure of the neural network is specified, and then the rest is learned in a sense. And that's also typical, I guess, for many of the neurosymbolic AI systems. It's all about learning the parameters of the neural networks, also learning the parameters of maybe some of the logical aspects. This is what most of Neuro-Symbolic is about. There is a few approaches starting to learn also the structure of the rules, but that is much, much harder. And the way it typically works is that they use a kind of template for a rule like X if Q, if Y and Z, and then would kind of look for all possible combinations that X, Y, and Z can be. And so they would kind of, generate all the possible rules and then score these rules. And the rules, most of the rules would not be interesting, so would get very, very low scores and would disappear from the program. But of course, that's very, expensive. There's more clever ways of doing that, but I don't think many have published on that yet. We're looking a little bit at ILP style things for doing that, but and also
So
soon
did you have rule learning in the stochastic DeepStochLog? Or did you have learning the probabilities, I guess, right? That's what
Yes,
you had
so
there.
we had rule learning for the deep probabilistic logics. That's what also for the other frameworks like Markov logic, there is like structure learning techniques. But with the neural networks, I mean, it becomes a lot to learn, the logic, the parameters, the neural networks, the structure. Also with PGMs, it's typical to focus mostly on parameter learning. So
Yeah. There was another question in the chat, Luke. Oh, I guess that's the question we just asked, right? Whether you looked at construction
yeah.
of the rules.
Well, I guess one of the ways to do it is what a lot of people do these days is like look at specify rules in language and or try to extract it from a large language model and put it into some kind of logic form. There's been a lot of progress on that. The advantage is that, well, the logic doesn't have to be perfect. I guess in the old days, when people were working with logic, everything had to be perfect, right? You wanted complete knowledge, you wanted everything to be consistent. If there was one mistake, it didn't work. I guess with these soft versions of logic, these probabilistic versions of logic, and the learning on top of that, it's much more flexible. Shouldn't hurt too much if you have too many rules, or if you have a few rules missing. Still, I think a few rules can speed up the learning, but it doesn't have to be complete or anything like that. So that's also one of the advantages of this kind of learning with neurosymbolic methods.
In the survey, did you identify any benchmarks or common ways to evaluate the performance of different NeSy systems? Or did you feel that there is indeed some differences in expressiveness? And so it's not easy to compare, say, regularization approaches with something like Prolog.
Oh, well, a lot of these have been, I mean, the standard benchmark is like this MNIST images. If you can do better, then it's typically Sudoku. There is some other data sets, like I like a lot this traffic data set from, although there it turns out that the knowledge doesn't help so much, that if you tweak enough on the computer vision part, that you're probably gonna do better. I think as an illustration, this is a key one. There is some other ones as well. So yeah, but I think it's mostly about predicting certain classes and stuff like that. So yes.
Look, I'm conscious of the time. You said you have to leave sharply
Yes.
at 3. So let's thank
Okay.
Luke, everybody, for a wonderful talk. And as usual, the talks will be uploaded to YouTube in case you missed a part of it. And see you next time. Thanks again,
Okay.
Luke, for agreeing.
Thanks. See you.
Bye.
Bye.